A single galaxy can stretch across millions of light years. The biggest one we've found is roughly 50 times larger than the Milky Way. That size flips our mental maps of the universe. Immediate takeaway: the universe organizes itself at scales we barely grasp. This video explains what that galaxy is and why it matters. First, a clear definition: it's a supergiant elliptical galaxy. Secondly, the stakes. It rewrites our ideas about cosmic growth. I'll show how astronomers measure that size and what it took. Example: IC 1101 sits inside a huge galaxy cluster, pulling neighbors. Quick mental image: the Milky Way would be a small dot nearby. Astronomers use deep imaging surveys combined with spectral data. Those measurements let them estimate physical diameter in light years. Concrete payoff: this is real size, not just bright halo illusions. Final recap: a supergiant galaxy exists and it's mind-stretching. IC 1101 is the canonical example of a supergiant elliptical galaxy. Astronomers discovered it at the center of Abell 2029 cluster. It shines with billions of old red stars and diffuse light. Definition: a galaxy dominated by a massive, smooth stellar envelope. The stakes are obvious. IC 1101 tests models of galactic growth. Mechanism: repeated mergers with other galaxies expand the stellar halo. The cluster's gravity pulls in satellites and strips stars outward. Simulations show cores merge and halos puff up over time. Example: observation. Deep images reveal faint light out to millions. Those images measured a diameter of several million light years. Compared to the Milky Way, it's tens to hundreds times larger. That scale changes our picture of galaxy ecosystems and interactions. Recap: IC 1101 is enormous, built by mergers inside a cluster. Measuring a galaxy that large challenges observational techniques. Definition: size means the extent of starlight above background. Stakes: without proper measurement, we misclassify structures and halos. Mechanism: astronomers use surface brightness profiles to define edges. They stack deep images, then subtract background sky glow carefully. Spectroscopy gives distance via redshift and confirms cluster membership. Example: Sloan Digital Sky Survey provided wide, deep images of IC 1101. Hubble helped resolve central structure and verify stellar populations. Those combined datasets let astronomers map light to huge radii. Concrete measurement: analysts define cutoffs at specific brightness levels. Then they convert angular extent to physical size using distance. This process minimizes bias from faint background galaxies and sky noise. Example: in real terms, measuring a faint halo equals spotting a candle from miles. Final recap: measuring giants demands depth, patience, and careful calibration. Giant galaxies grow by swallowing smaller galaxies over billions of years. Definition: galactic cannibalism means mergers in large stellar envelopes. Stakes: growth patterns tell us about dark matter distribution and feedback. Mechanism: in dense clusters, galaxies experience repeated close encounters. Tidal forces strip stars and deposit them into extended halos. Major mergers build cores, while minor mergers puff up outskirts slowly. Example: ICS, the intracluster light, originates from stripped stars. IC 1101 displays a vast intracluster component and diffuse glow. Simulated universes reproduce these giants when clusters are massive. Concrete case: one simulation showed halos grow after repeated mergers. Dark matter halos act like scaffolding and pull in baryonic matter. Observationally, we see streams and shells that trace past collisions. Final recap: cannibalism and tidal stripping create supergiant stellar halos. Comparisons help comprehension. The Milky Way is a useful benchmark. Definition: the Milky Way spans about 100,000 light years. Stakes: knowing ratios turns abstract millions into relatable multiples. Mechanism: divide sizes to see how many Milky Ways fit inside. IC 1101 could contain tens of thousands of Milky Way-sized galaxies. Concrete image: if the Milky Way were a small dinner plate, then IC 1101 would cover hundreds of nearby stadiums in scale. Example: in real terms, the Andromeda galaxy is twice the Milky Way's diameter. Yet IC 1101 dwarfs both by orders of magnitude. Put differently, our galaxy would vanish inside a single IC 1101 arm, an everyday analogy. One grain of sand compared to a beach. Final recap, comparing to the Milky Way makes giant scales tangible. Discovering such giants affects models of cosmic structure formation. Definition: cosmological models predict how matter clusters over time. Stakes: large galaxies test the limits of those predictions and parameters. Mechanism: hierarchical clustering creates small objects first and larger ones later. If giants like IC 1101 exist early, models require faster growth. Astronomers compare observed abundance to simulations and refine physics. Example: adjusting merger rates changes the predicted number of giants. This impacts dark matter halo mass functions and feedback prescriptions. Concrete implication: accurate giant counts constrain cosmological parameters tightly. They especially test how baryons respond to energetic feedback processes. Observations of IC 1101 stellar populations reveal ancient formation epochs. Final recap: every giant tightens constraints on galaxy formation theory. Massive galaxies often host enormous central black holes. Definition: a supermassive black hole controls central dynamics and energy output. Stakes: black hole feedback can regulate star formation across the galaxy. Mechanism: active accretion drives winds and jets that heat gas. When gas is heated, star formation often slows or shuts down. Example: cores of giant ellipticals show old stars and little cold gas. IC 1101 likely contains a very massive black hole, influencing evolution. Concrete estimate: central mass scales with bulge properties in known relations. Measuring that black hole tests feedback models and growth histories. X-ray observations reveal hot gas halos that indicate past energetic events. Radio jets can clear central regions and alter star formation efficiency. Final recap: black hole feedback is central to giant galaxy evolution. Finding and measuring giants faces observational hurdles and biases. Definition: observational bias means we may miss faint extended light. Stakes: missing these halos would underestimate mass and influence. Mechanism: sky brightness, instrument sensitivity, and image processing matter greatly. Deep surveys require long exposures and careful calibration techniques. Example: upcoming telescopes will map faint outskirts with unprecedented depth. The Vera Rubin Observatory will produce wide, deep imaging for large samples. JWST helps study stellar populations in more distant, compact giants. Concrete future: combined datasets will refine size estimates dramatically. This will tell if IC 1101 is an outlier or a trend. Large samples will allow statistical statements on giant frequencies. Astronomers will then test whether cluster environment predicts giants. Final recap: technology and surveys will reveal the true population. That huge galaxy flips our sense of cosmic proportions and wonder. We saw what it is and why it matters to theories. We explained how astronomers measure its diameter with care. We showed growth mechanisms like mergers, stripping, and feedback. We compared scales to the Milky Way to make sizes relatable. Future telescopes will sharpen measurements and expand statistics. Final anchor: the universe is bigger and stranger than we imagine. Immediate payoff reminder: gigantic galaxies exist and they reshape theory. Thanks for staying curious and for looking up with me tonight. The scale we discussed matters for fundamental questions about origins. Each measurement tightens our models and deepens our curiosity. The sky hides more giants and future surveys will reveal them. Anchor sentence: remember, the biggest galaxy we found defies ordinary imagination. Gentle request: subscribe for calm, curious explorations of the cosmos.